Hello?
Yes, sir.
Yes. So, before we start today's class, how was the examination? How was the examination? Good, bad, worst? Any comments?
Sir, it was okay.
It was okay. All right, good. So I think the highest is 24 or 26. I think one or two students got 24 or 26. That is the highest. But I can see that a very good Gaussian curve I have obtained. So that seems the examination was okay. But just to give you the solution of the all the questions, was there any doubt on any question? I thought everything was simple. Uh, One step answer for most of the cases, isn't it?
Yes, sir.
So I will just quickly take 2-3 minutes and you know uh, revisit the answers for all the questions, and then we will start with today's class. Okay, so the first question was this: a hollow cylinder with internal diameter of 5 centimeter and outer diameter of 10 centimeter. So these values 5 centimeter, 10 centimeter, these were different for different students. Okay, has an inner surface temperature of 200 degrees Celsius and the outer surface temperature of 100 degrees Celsius. Determine the temperature in degrees Celsius of the point halfway between the inner and outer surface. So this halfway, this part, if somebody has looked at this carefully, then he got the answers correctly. Okay, so we can write down we can find out the halfway radius as this, and then we can assume that the steady state heat transfer is there. So Q will be same, so we can write the expression for Q for the entire thing and halfway through, isn't it? And just rearranging that, we can find out the temperature at the halfway. Okay, so the temperature at halfway we can obtain directly by using this equation. Is it clear to everyone?
Yes,
Hello?
sir.
Yes, sir.
Okay, all right. The next question was in the next question there's a 40 cm thick furnace wall with temperature surface temperature of 300 degrees Celsius and 50 degrees Celsius. The thermal conductivity K is given as the thermal conductivity was not constant, it was a function of temperature, uh, and the heat loss per unit area is been asked to calculate. Okay, so the only complication in this particular question was the thermal conductivity was a function of temperature. Okay, so if you put it in this equation directly and integrate, you should get it. Okay, that is also has one step answer. Is it clear to everyone this part, second question?
Yes, sir.
Third question, again the heat transfer through a composite slab we wanted to calculate. The only complication we had is this block B and block C. If you look at the geometry of that, unlike the all other blocks, the cross sectional area of B and C were half, and if you look at the resistance of B and C, this is instead of the series resistance, in this case the heat transfer resistance will be parallel. So that was the only catch. Somebody understood this particular concept, then he should have got the answer correctly. Okay, so because of this, that the resistance of block B and block C are parallel, we have to use this equation. Like if you wanted to take the total resistance of this BC block, then it will be 1 by RBC will be equals to 1 by RB plus 1 by RC, and uh, the 1 by and the resistance of these individual blocks can be obtained by using this equation, isn't it? Length divided by K thermal conductivity into A. Okay, so with this one can obtain the heat transfer through this entire block. Isn't that was the only catch, isn't it? So is it clear to everyone? This part?
Yes, sir.
Yes, sir.
Question 4, I think many people have done question 4 wrongly, primarily because they have used the same equation blindly which was there in the slide. Maybe I'll just go back. Okay, I'll just show the conduction slides, then you will understand why I'm saying that many people have made the mistake. Okay, so see. So this was the situation given in the slides, isn't it? So temperature T1 here and temperature T2 here both were different for the case which we have studied in the class. But the question which is given in the problem, this temperature T1 and T2 both were same. This was ambient here, isn't it? Correct. So in that case, that symmetry concept of symmetry has to be used. What I mean by that is you have to start the origin from L/2 here. Okay, and then you should have taken the length on the left hand side as minus L/2 and on the right hand side L/2, because that symmetry will be maintained because temperature here T1 and T2 both are same. That was the only catch. That was the only catch. If you have got that, then things became easy, because this is what the final expression you are going to get. The only problem comes in the boundary conditions. The boundary conditions in the other case will be the case which is given in the problem would be at the center when x equals to 0, the temperature dt by dx will be 0. That will be the one boundary condition, and another boundary condition will be at x equals to minus L/2 or plus L/2, the temperature will be Tw. So with that, if you put those other two boundary conditions, this equation number 3 is going to get simplified immensely. And finally, what you are going to get is the equation which I have shown in the doc file. So these are the equations you are going to get with that. Okay, so the wall temperature will be given by this equation, first equation, whereas the maximum temperature will be at the center. That will be given as Tw plus psi V L square by 8K. This is just a one-step answers. You can start from that final equation, put the new boundary condition, and you will get these two equations. That's it. But I think very few people have cracked this. So this is the only question which is attempted by correctly done by few students, only few students. Okay. Question number 5, again same. You have to use the same formula which we have derived earlier and get the answer. There is no complication in this. Is it clear to everyone?
Yes, sir.
Question 6, again straightforward. I thought everybody should have done this, but I think few students still missed. So doesn't matter if you have missed. Please do your, please go through the material carefully next time. So in this question, the concrete wall is given, and then we were looking at convection in addition to conduction. So therefore, this Q by A will have a convection term. So convection resistance will be given by 1 by Hi. Outside convection resistance will be given by 1 by H0. And since area is constant in this case, that area we can directly take it in the numerator here, and that comes out on the denominator here on the left hand side. So directly we get delta T divided by 1 by Hi plus L by K plus 1 by H0. So one step answer. Last question I have given, this last question I have given only because I wanted you to score. But still some students got 0 marks. So that is the clear, that is the alarming situation, isn't it? If you have got the 0 in this first question, then in the 7th question, then definitely you need to go through material carefully. You have to take this course seriously. Even if you are not able to solve this last question, which I have given only for scoring the marks, then there is a serious problem. Okay, that is what my suggestion is. All right. But again, I am saying this, whether you got good marks or bad marks, that is not the reflection of your intelligence. That is only the reflection of how seriously you are taking this course, how much hard work you are putting in. Okay. Once you have set a foot in this institute, that intelligence was guaranteed. Okay. There's no question about the intelligence. Question is all about, your seriousness and hard work. That's it. That is the only thing is missing if you are not getting good marks. Other than that, I think you all are intelligent. All right, so let's start with where we have left. Is there any question?
Sir, excuse me, sir. I had a doubt in fourth question.
Please go ahead. In fourth question, okay.
Yes, sir.
What is the doubt?
Sir, actually, it was regarding the dimensions of psi v. Shouldn't it be watt per meter cube? That's what confused me in this question.
Yes, sir. Same problem.
In first sentence.
Yes, sir.
What you are saying?
Sir, in the first sentence, the rate of heat generation, shouldn't the dimensions be 4 into 10 to the power 4 watt per meter cube? That's what confused me in this question.
Okay, I will check. I think this is correct,
That's
but
why
I will still check. Okay. All right.
Sure.
1 minute. हेलो, हाँ सर बोलिए. सर क्लास में हूँ, बताइए. अच्छा, ओके. Okay, okay, sir. Okay. All right. So I will check. Okay. All right. Let's go back to our slides. Okay, so in the last class, what we have covered so far is the slides visible to everyone?
Yes, sir.
So this was the problem we started looking at. Did we complete this part? Did we complete this entire thing till this point?
Yes, sir.
Okay, okay. I think in the last class what we have discussed is if there is a laminar flow through a tube and simultaneously there is a heat transfer from the wall of the tube, how the Nusselt number will be related. That is what the things which we are trying to look at. Why we have tried to solve this simple problem? Because we said that even for a simple problem like this, a complicated analytical complicated analysis we have to do, and finally we will get the solution. But think about the realistic case when there is a turbulent flow. It will not be easy to solve. That's what we have said. And just to appreciate that, we have solved the simple case with the first principle approach. Okay. So what we have seen here is if you are assuming this thing that the constant wall heat flux is there, if you are assuming that the constant wall heat flux is there, in that case, the Nusselt number comes out to be 4.364. But if you assume that the constant wall temperature is there, and if you solve this entire problem again, then you will get the Nusselt number equals to 3.66. So all the correlations, you will see that all the correlations for laminar flow through the circular pipe, you will see that for a constant heat flux, you will get the correlations which will start with 4.364 and some additional factors you will have. That is what we have seen here also, isn't it? See the correlation here, this is for a constant temperature. So that's why it is started with 3.66. But if you see other correlations which are for the constant wall heat flux, then this correlation will start from 4.364. Okay. So these numbers which are used in these correlations are not completely arbitrary. There is some logic behind it. Okay. Also, what are the dimensionless groups should be there in the correlation that you can find out directly from the dimensional analysis. Okay. So up to this we have seen in the last class. Now, so see, very often what we get is we have a non-circular ducts. So see, all these correlations are developed for a regular geometry. It could be circular or a flow path cylinder or a flow path sphere, etc. Isn't it? But when we are having a non-regular geometry like non-circular ducts, in that case, how to use these correlations? In such cases, what we have to do is we have to find out the equivalent diameter and then assume that equivalent diameter and use the correlations which are derived for the circular duct. Is it clear to everyone? This is the standard practice we also do in fluid mechanics, isn't it? So we find out the equivalent diameter. Equivalent diameter is nothing but 4 into hydraulic radius, and hydraulic radius is defined as a cross-sectional area of the flow divided by weighted perimeter. So in this case, let's say if you are having a rectangular duct with the sides L1 and L2, in that case, what will be the cross-sectional area of the flow? L1 into L2 multiplied by 4. This 4 will be just because of this, isn't it? Equivalent diameter is 4 into hydraulic radius. So this 4 factor is coming from this. So L1 into L2 is the cross-sectional area of the flow divided by weighted perimeters. And weighted perimeter in this case will be what? 2 L1 plus L2, isn't it? That will be the weighted perimeter. But now the question is, so see, this weighted perimeter for the pressure calculation and the weighted perimeter for the heat transfer calculation may be different. It may not be same. For instance, let's say if you are taking the case of annular flow, let's say double pipe heat exchanger we have taken. Let's say this is the classical example of the double pipe heat exchanger. So there is one fluid is flowing through the inner tube here. Let's say which is shown by this red colored tube here, and another fluid is flowing through this annular region. Okay, so for the fluid which is flowing through the inner tube, there is no problem because it's already a circular duct. But what about the flow through the annular region? We have to find out the equivalent diameter and then the hydraulic radius and the equivalent diameter. Do you all agree? Yes or no?
Yes, sir.
So in this case, so see, if you look at the cross section, how the cross section will look like. The inner pipe will be this, isn't it? And outside this, you will have so isn't it this in this way you will get, so this inner is already circular. It doesn't look circular, but you can assume that it's circular. Okay, so this inner pipe there is no problem, but what will be the equivalent diameter for this outside annular region, isn't it? Again, for a pressure calculation, this hydraulic radius, and for a heat transfer calculation, the hydraulic radius is going to be different. Why I'm saying this? Because for a pressure calculation, pressure is acting symmetrically everywhere in this entire cross section. In this entire cross section, the pressure is acting symmetrically. Do you all agree? Yes or no?
Yes, sir.
But if you are taking the heat transfer is taking place only at this location, isn't it? At this boundary, it's not taking place here, isn't it? It's not taking place here. So for heat transfer, the weighted perimeter will be what? Only this outside area of this isn't it? Only this area will be the weighted perimeter. In case of pressure calculation, both this area as well as this entire thing becomes the weighted perimeter, isn't it? But for a heat transfer, only this part becomes the weighted perimeter. Only this part becomes the weighted perimeter. So clearly the hydraulic radius for pressure calculation and for a heat transfer calculation both are different. So that's what we have done here. You can see here for a pressure drop calculation here the denominator, which is nothing but the weighted perimeter, is given as pi d1 plus pi d2, isn't it? Because both this surface and this surface, both surfaces are important for pressure calculation. For heat transfer, only this surface is important. That's why only pi d1 is there in the denominator. Numerator, again the difference between the area, that is what we have done. Pi by 4 d2 square minus d1 square. So that is the difference between this area. That will be the total surface area, cross-sectional area of the flow. Is it clear to everyone what we have done here? Hello?
Yes, sir.
All right. Okay. All right. So once we can find out the equivalent diameter for the non-regular surfaces, then we can use the correlations which are developed for the circular geometry, isn't it? So again, in addition to that, some correlations for the heat transfer for the external flow is given. So far we were talking about the transfer for internal flow, isn't it? All these correlations are for flow of the fluid through the pipe, inside the pipe. We are not saying the flow of the fluid across the pipe. Across the pipe means the cylindrical geometry is there and over that you are blowing the air or some other fluid, isn't it? That type of situation we have not covered so far. So let's look at the heat transfer correlation for external flow. So this is, if you are looking at the flow over a flat plate, so the correlation for the laminar boundary layer, this is the correlation. If you remember, that is the same correlation which we have used in one of the tutorial question, isn't it? Last to last tutorial, isn't it? So Nusselt number is given by 0.332 REX raised to the power 1 by 2, Prandtl number raised to the power 1 by 3. So here why we have given REX. REX is nothing but Reynolds number calculated in terms of the distance from the leading edge. So X is the distance from the leading edge. Okay, and these are the limits given. So Prandtl number should be between 0.5 to 50 and Reynolds number should be less than 5 into 10 raised to the power 5. This is the critical Reynolds number which we have talked about earlier. In a turbulent zone, we can use 0.0296. Reynolds number raised to the power 4 by 5 and Prandtl number raised to the power 1 by 3. And again, this is valid for Prandtl number between 0.6 to 60 and Reynolds number between 5 into 10 raised to power 5 to 10 raised to power 7. Again, the correlation for a flow path cylinder. So if you are having a flow path cylinder, then the Nusselt number is calculated in terms of the diameter of the cylinder. So that's why it is given as NUD. So that is given as HD by K is given by this particular correlation. Again, this correlation is valid between the Reynolds number between 0.1 and 10 raised to power 5. Okay. For a flow path sphere, the expression is given by Whittaker and that is given as NUD, which is nothing but Nusselt number in terms of diameter of the sphere. That is given as HD by K and it is equals to 2 plus this complicated thing here, isn't it? Again, one thing to note down, if you calculate the Nusselt number for a Stokes flow, you can analytically prove that Nusselt number for a Stokes flow comes out to be 2. This can be proven analytically. Okay, it's not difficult. Try yourself, see. Okay, you should get the Nusselt number equals to 2. So remember, in this case also we have started with some basics, isn't it? And then we have proven that the Nusselt number for the constant wall heat flux comes out to be 4.364. In a similar manner, if you do the analysis, then you will get the Nusselt number equals to 2 when we are looking at the flow past the sphere. So that's why this correlation is starting from 2 plus something. And from dimensional analysis, you can find out that Nusselt number is related with Reynolds number and Prandtl number. So that's why these two things are present in this correlation. But how these are related, dimensional analysis is silent on that. So therefore, you can have any complicated correlation, provided that it includes only the Reynolds number and Prandtl number. Is it clear to everyone?
Sir, I have a doubt, sir. In the previous question, like you said, if we take the case of pressure, then we take the weighted parameter, and that of heat transfer, the weighted parameters are different for both. Sir, can you explain that one more time?
Here you can see that the for heat transfer only this surface area becomes important, isn't it? The surface area outside the inner tube, that becomes important for heat transfer. But for a pipe flow, not only this surface area becomes important, but also the surface area here. That's why it is pi d1 plus pi d2. Remember, pi d2 is the weighted perimeter with respect to this the inner surface area of the outer tube, isn't it?
Yes, sir.
So that becomes important in the pressure calculation. But for a heat transfer is taking place only here, isn't it? Between this. So that's why only pi d1 is coming in.
Pressure calculation, by that, what you are trying to say, like the pressure difference or what?
So remember, if you start solving the velocity distribution here, you will be looking at the pressure, isn't it? So you will be looking at the pressure in this entire region, isn't it? So that depends not only this surface area, but also this surface area. Okay, isn't it? Because pressure will be acting in this entire region here, isn't it? Right. But for a heat transfer calculation, the heat transfer is taking place only between these two. It's not, we are not accounting this heat transfer here so far. So that's why for a heat transfer calculation, the equivalent diameter will have only pi d1 and not pi d2. This pi d2 term is not being used here. Is it clear, Achintya?
Yes, sir. Got it.
Okay. Again, I have given only few correlations. There are multiple correlations present in the book, and students are advised to refer the book for additional correlations. Okay. Let's look at another interesting case. This is the commonly used, case for removing the heat in several industries. Okay, in several industries. So in this problem, what is happening is the hot fluid is hot fluid or a cold fluid, doesn't matter. So let's assume that the hot fluid is flowing through these tubes. Okay, and these tubes are perpendicular to the plane of your screen. Okay, but the air is blown across these tubes. Across these tubes means the air is blown parallel to your screen. Air is blown parallel to your screen, whereas the fluid is flowing through these tubes perpendicular to the plane of your screen. Okay, so in this case, there are two designs are there. First one is the aligned design. So aligned design, you can see this, that it is properly arranged, isn't it? Whereas there is another design which is called as a staggered design. So in the staggered design, you can see that these are arranged in a slightly different way. Okay. So in a aligned design, two parameters are important. One is the longitudinal pitch. So longitudinal pitch is this particular distance, isn't it? Whereas the transverse pitch is the distance between two tubes in a vertical direction. Okay. But if you look at the staggered arrangement, in the staggered arrangement, the transverse pitch is between the two tubes in the same column. But you can see that this will be twice the transverse pitch present in the aligned arrangement. Remember, in the aligned arrangement, this particular tube would be here in between here, isn't it? And therefore, in general, the transverse pitch is twice in the aligned arrangement compared to the staggered sorry, the transverse pitch in the staggered arrangement will be twice the that of the aligned arrangement. Another thing is as we blow the air across this
So could you
bank
explain
of
that
this
again?
tube. Hello,
So why is it twice?
you can see the geometry here. See, in a normal case, in a normal aligned case, this particular tube would be here in between,
Oh, okay, okay. Thanks.
isn't it? So, okay, so as the air is blown over the tube in order to cool the fluid which is flowing through the tubes, what will happen is the temperature difference at this end will be higher, and as we move along this bank of the tube, the temperature difference or a driving force is going to decrease. Do you all agree? Hello? As we move along the bank of this tube, this difference is going to reduce, isn't it? Yes or no?
Yes, sir.
Okay. All right. Now in this case, in both these cases, the driving force is going to decrease. And remember, when the driving force is going to decrease along the length, what type of temperature difference we use? What type of temperature difference we use? See, this is what we said here. The temperature difference is going to vary along the length of the tube. In that case, what temperature difference we use here? Log mean temperature difference. We will prove today, towards the end, in today's class, we will prove that this indeed is a log mean temperature difference. But whenever the driving force is decreasing or increasing or changing along the length, in that case, the log mean temperature difference has to be used. Okay. All right. Is it clear to everyone? Yes or no? Hello?
Yes, sir.
So for this particular system, again, the correlations given by this particular equation, Nusselt number is given by HD by K. Here Nusselt number is calculated in terms of the diameter of the tube. That's why it is represented as NUD. That is given as C into RED max raised to the power m, Prandtl number raised to the power 0.36, and Prandtl number divided by Prandtl number at wall raised to the power 0.25. Here RED max is nothing but the Reynolds number calculated in terms of diameter of tube, and also the velocity taken as a maximum velocity. Velocity is taken as a maximum velocity. So maximum velocity will be somewhere here in between, isn't it? Where the cross-sectional area is the lowest. Do you all agree? Isn't it?
Yes, sir.
So the maximum velocity is calculated for both aligned arrangement and a staggered arrangement using this particular equation. So Vmax is given as St divided by Sd minus d into V. Similarly, Vmax is calculated as Sd divided by 2 by St divided by 2 into Sd minus d into V in terms of the staggered arrangement. Okay. Now what we do is first we calculate the Reynolds number. Then we check the Reynolds number in these ranges, whether the configuration is aligned or is staggered. Also, we calculate St by SL, and depending on that, we select the coefficient C, capital C and M. And those coefficients C and M given in this table are used in this correlation, and then the Nusselt number is calculated. Okay, again, as I said, the temperature difference in this case has to be calculated as a log mean temperature difference, because the driving force is going to vary as we move from left hand side of this bank of the tube to the right hand side of the bank of the tube. Okay, as we move from left hand side to right hand side, the driving force, which is nothing but the temperature of the fluid which is inside this tube and the temperature of the air which is being blown here, that temperature difference is going to vary. We can assume that the temperature of the fluid which is flowing through these tubes is constant, but the temperature of this blown air is going to decrease as we move along, because this air is going to get heated or cooled down depending on whether we are looking at heating or cooling. Do you all agree? Does it make sense what I'm saying?
Yes, sir.
So this type of cooling or heating is regularly cooling. In fact, this is primarily used for cooling. So this type of cooling of, so see, this is the commonly used for cooling the the gases coming out from the power plants. Okay, so hot gases coming from the power plant passes through these tubes. Okay, and the cold air is blown across these tubes in order to cool the hot gases coming out. Okay, so you can see that the temperature of this cold fluid will increase or decrease depending on whether you are looking at the temperature, whether you are looking at the cooling or heating in this arrangement. Okay, all right. So similar to that, if you are looking at, let's say, the flow through the packed bed. Flow through the packed bed we regularly use when we are using packed column or a fluidized column, isn't it? This is the commonly used reactor in the process industry, isn't it? So when we are using the packed bed, the heat transfer is related through this equation. Here you can see that epsilon is the voidage factor. St is a Stanton number into Prandtl number raised to the power 2/3, and that is given as 2.06. Reynolds number raised to the power minus 0.575. Here Reynolds number is calculated in terms of the diameter of the particles. That's why it is written as REdP. Here dP is nothing but diameter of the particle. REdP is calculated as diameter of the particle V naught rho divided by mu, where V naught is nothing but superficial velocity. Okay. Again, for a fluidized bed, the equation given here, Nusselt number in terms of diameter of the particle is given as HDP by K, and it is starting from this coefficient 2. Remember, as I said, when we are having the flow across the spherical particles, this 2 comes, because if you are taking the Stokes law, for a Stokes law, Nusselt number will be given by just 2, isn't it? All right, is it clear to everyone?
Sir, what is the difference between packed bed and fluidized bed? Means what?
So in a packed bed, particles are not freely suspended. In a fluidized bed, the particles are freely suspended because of the fluidization effect, isn't it? Is it clear?
So based on that concept, we are modifying these equations.
So there is a difference between packed bed and fluidized bed. In a fluidized bed, what happens is you increase the velocity of the fluid blown from the bottom, and because of that, the higher the velocity, the pressure drop across the particle becomes same as the weight of the particle, and because of that, the particles get freely suspended in the fluid medium, and in such situation, the bed is called as fluidized bed. But in a packed bed, that situation is not there. So you are having a catalyst particles packed inside the bed, and then you are flowing the liquid or a air through that bed, isn't it? Liquid or a gas through that medium. In this case, we are not ensuring that the particles are freely suspended. We are not ensuring that. Is it clear?
Yes, sir. Yes.
Okay. Okay, so this is the concept I was talking about. So as I said that so far what we have looked at the heat transfer. So calculation of the heat transfer becomes extremely easy if the heat transfer area is constant, if the driving force is not changing across the length, and the heat transfer coefficient is also constant. Overall heat transfer coefficient is also constant. In that case, heat transfer becomes very simple, isn't it? Then you can write down HA delta T. That's it. Yes or no? The amount of heat transferred can be given by Newton's law of cooling directly as HA delta T, isn't it? Where H is the average heat transfer coefficient, which is not changing. Overall heat transfer coefficient H is not changing. A area is also not changing, and delta T is also not changing. But very often you will see that all these parameter changes. For instance, if you are looking at the boundary layer, concept of boundary layer, in the concept of boundary layer, the heat transfer coefficient H is varying. Isn't it? If you are looking at the cylindrical or a spherical geometry, then your area of the heat transfer is changing. And if you are looking at the heat transfer between a double pipe, etc., a similar example shown here, you can see that the delta T is also changing across the length. Isn't it? So your life becomes, difficult if there is a variation in H, there is a variation in area, and there is a variation in delta T. Yes or no? Do you all agree?
Yes, sir.
Yes, sir.
So far we have looked at two cases. We have looked at how to account if there is a change in the heat transfer coefficient. When there is a change in the heat transfer coefficient, how we have accounted? We said that we will not look at the local heat transfer coefficient, rather we will calculate a average heat transfer coefficient and we will work out with that. Do you all agree? Yes or no? That's why all the correlations you can see that these are given in terms of overall heat transfer coefficient, average heat transfer coefficient. Yes or no?
Yes, sir.
Again, the complications comes when there is a heat transfer associated, there is a convection and conduction, both are associated. Even radiation is associated. In such cases, individual resistances has to be used in order to calculate the overall heat transfer coefficient. Isn't it? So even such situation also we have seen, and in such cases, the overall heat transfer coefficient U has to be used instead of just small h. Even such cases also we have seen so far. Do you all agree? Yes or no? Do you all agree?
Yes, sir.
Okay. Now, the only thing which we have not looked at so far is when there is a change in the driving force. Of course, we have taken the log mean temperature difference directly, but let's try to derive that and let's look at how my heat transfer is going to vary if I am not having the same constant temperature difference across the length. Okay, so let's look at both these concepts little bit in more detail. So in order to appreciate that, we have considered a simple double pipe heat exchanger again. So this is a simple double pipe heat exchanger, but we are assuming a co-current flow. Co-current flow means the hot fluid and the cold fluid, both these fluids are flowing in a same direction. So you can see that the hot fluid is flowing through the inner tube here, whereas the cold fluid is flowing through the annular region, and both are flowing in the same direction. That's why we are calling it as a co-current flow. So this particular end is represented as end 1. This particular end is represented as end 2. Now at end 1, what will be the temperature difference or what will be the driving force here? Driving force will be TH1 minus TC1. Isn't it? TH1 minus TC1. This will be the driving force. Do you all agree at this end? Yes or no? Hello?
Yes, sir.
Yes, sir.
And this driving force we have taken as delta T. So let's say this, let's represent this delta T1. This subscript 1 represents the driving force at end 1. Okay. Now this driving force, as we move along the length of this double pipe heat exchanger, you can see that this delta T is changing. You can see this delta T is decreasing, isn't it? So at the end 2, the delta T is delta T2. Do you all agree? Do you all agree? And this delta T will be lower than delta T1. Why? Because as the fluid moves from this end 1 to end 2, by that time, by that distance, you can see some heat will be transferred by the hot fluid to the cold fluid. And because of that, the temperature of the hot fluid is going to decrease, whereas the temperature of the cold fluid is going to increase. And because of that, this delta T is going to decrease as you move along the length of the double pipe heat exchanger. Do you all agree or not? Does it make sense what I'm saying?
Yes, sir.
So this delta T is decreasing. Remember here delta T is a higher value, delta T1 is a higher value, and this difference is a higher value. Remember this difference is a higher value here. But as we move along the length, you can see this delta T2 will be a smaller value. Yes or no? But the important thing to note down here is you can see that the outlet temperature of the cold fluid will be always lower than the outlet temperature of the hot fluid. So this TC2 will always be lower than TH2. Why? Or at max it can approach to this value because you will have some heat transfer resistance present here. So TC2 will not become TH2, isn't it? So outlet temperature of the cold fluid will not exceed beyond the outlet temperature of the hot fluid in case of the co-current flow. Do you all agree or not? What I'm saying is TH2, TC2 will not become more than TH2. That's what I'm saying. Do you all agree or not? Hello?
Yes, sir.
But let's look at the another arrangement. Now in this another arrangement, what we are doing is we are looking at counter current flow of the both the fluids. So hot fluid is again flowing through the inner tube, whereas the cold fluid is flowing through the annular region, but their direction of the flow is opposite. So the cold fluid is entering at end 1 and leaving at end 2, whereas hot fluid is entering at end 2 and leaving at end 1. Now here you can see that the outlet temperature of the cold fluid can be higher than the outlet temperature of the hot fluid. That means TC2 can be higher than TH1. This TC2 can be higher than TH1. Can you see the point? Yes or no?
Yes, sir.
This TC2 can be higher than TH1. It doesn't matter. There is no problem in that, isn't it? So that is what one of the question was there in your tutorial where we have stopped in the last tutorial. Remember, I said that in this case only the counter current contacting is possible. Co-current contacting is not possible because there the outlet temperature of the cold fluid was equals to the outlet temperature of the hot fluid, and such situation can occur only if I am having the counter current heat flow. Otherwise, it is not possible. So just by looking at those temperature itself, I have concluded that in this case, the counter current contacting is there and not the co-current contacting. Do you all agree? Yes or no? So in this case, this outer temperature TC2 can be greater than the outer temperature of the hot fluid. Can be. This word can be is very important. It's not that always it will be higher. It could be lower also, but it can be higher also. That's what we can say. Correct? Okay, so now here you can see that the delta T1, now the change in the temperature or a driving force at end 1 will be what? TH1 minus TC1. The driving force at the end 2 will be what? TH2 minus TC2, isn't it? And more or less this delta T remains, more or less around the same order. Unlike the previous case here, you can see this delta T is decreasing as we move. So unlike this co-current flow, in a counter current flow, this driving force is maintained at a specific value, nearly the same value. Okay, it may not be always true, but around the same order of magnitude, the delta T will be maintained. So this is also one of the reasons why the counter current flow gives a better heat transfer compared to the co-current flow. Okay, is it clear to everyone? Yes or no? Is it clear? Does it make sense? Hello?
Yes, sir.
That confidence is lacking.
Sir?
Please go ahead.
Sir, I had one query. So in this counter current flow, why temperature of both the fluid is increasing? Like, if like the
No. You look at the arrows. Look at the arrows. Hot fluid is
sorry,
started from N2
yeah.
and it is decreasing. as it moves. The cold fluid is starting from end 1 and going to end 2. That's why you can see the cold fluid is starting from end 1, coming out at end 2. Hot fluid is starting from end 2 and coming out at end 1.
Okay, so temperature difference is being measured at a specific location and not a specific time. Yeah.
No, it is with respect to the locations, isn't it? So driving, what will be the driving force here? This hot fluid is in contact with the cold fluid which is present here, isn't it?
Okay, sir.
So what will be the delta T1, delta T2 here? TC2 minus TH2 minus TC2, isn't it?
Yes, sir. Thank you, sir.
Okay.
Hello, sir. Hello.
Please go ahead.
Sir, this counter current flow is an example of a variable driving force or not? Because here delta T is almost constant.
No. So see, this comes looks same, but it is not always exactly the same. It will have some variation, but of course the kind of variation you will see here, compared to that, the variation in delta T will be slightly lower in the counter current flow compared to the co-current flow. Here you can see this delta T1 is very high initially, but then it becomes very small at the end. But unlike that, in a counter current flow, the delta T is more or less remains at around the same value, but it is not same exactly. Some variation will be there, depending on what value of CP you are having. Got the point? Depending on what value of specific heat for individual fluid you are having, this delta T will have some variation. All right. Hello. Hello. Does it make sense?
Yes, sir.
It will not be exactly the same. OK. All right. So now, after looking at these two, flow patterns, contacting patterns, let's look at the concept of, log mean temperature difference. So in order to derive the log mean temperature difference, we are starting with the co-current flow. But of course, the same equation you will get even if you start deriving with counter current flow. But we are deriving only with co-current flow. So let's look at the co-current flow again. OK. So if we apply the, so remember in this case, since this delta T is going to vary across the length, even though the cross-sectional area, in this case, this area is going to be, the heat transfer area will be along the complete length. But since this delta T is going to vary across the length, we have to take a shell here and do the shell balance. Is it clear to everyone? So reason for doing the shell balance is delta T is going to vary across the length. So let's take a small shell of the area dA. OK. And we are, trying to balance all the terms across this shell. So applying the heat balance over a small area dA of a co-current flow case, what will be dq? Dq is nothing but the heat transfer present in this small area. OK, so now in this small area, there are three types of heat transfers are there. OK, if I look at, maybe I just go back here. There are three types of heat transfer. One is the direct heat transfer between the hot fluid and cold fluid, which is occurring here, isn't it? That is one thing. So we can calculate how much heat transfer is taking place, but that the same heat transfer I can calculate just by looking at the sensible heat across these 2 points, isn't it? Yes or no? How much heat lost by the hot fluid is same as the how much heat gained by the cold fluid, and it is same as the amount of heat transfer across the hot and cold fluid. Do you all agree? So these are the three terms. How much amount of heat lost by the hot fluid, that will be given by MC MH CPH delta T, isn't it? How much heat gained by the cold fluid will be given by MC CPC delta T, isn't it? And how much heat transport between hot and cold fluid will be given by what? HA delta T, HA delta T LMTD, isn't it? So these are the three factors, and we are going to play with these three factors. Is it clear to everyone what I'm saying? Hello? Is it clear, or do you want me to explain again? So see, heat transfer here is taking place between cold and hot fluid here, but this heat transfer taking place between cold and hot fluid is same as the sensible heat gained by the cold fluid, and it is also equals to the sensible heat lost by the hot fluid, isn't it? Sensible heat lost by the hot fluid will be given by what? MHCpH delta T. Sensible heat gained by the cold fluid will be what? MCCpC delta T. And what will be the heat transfer between these two fluids? HA delta T LMTD. So these are the three terms which we are looking at with respect to this small shell we have considered. Okay. Okay, so in this case, this dq is given as U dA TH minus TC. So this is nothing but the heat transfer taking place between cold and hot fluid. Do you all agree? Yes or no? This is the heat transfer taking place hot and cold fluid. U dA TH minus TC, where U is the overall heat transfer coefficient, dA is the area of the shell, TH minus TC is the temperature difference between hot and cold fluid in that shell which we have assumed, isn't it? Do you all agree? Yes or no?
Yes, sir.
And this is same as this dq will be same as what? Sensible heat lost by the hot fluid. So that is MHCpH DTH, where DTH is the how much temperature difference taking place only in terms of the hot fluid. Similarly, MCCpC is the amount of heat gained by the cold fluid into DTC. So amount of sensible heat gained by the cold fluid, isn't it? Do you all agree?
Yes, sir.
Okay, so now here this first equation is represented as U dA delta T, and the second equation is minus MHCpH delta TH is same as MCCpC DTC. Here minus sign is there because as we are moving along the length, the temperature is decreases. Therefore, this minus sign is there because this DTH is decreasing as we are moving along the length. Therefore, this minus sign is coming in this case. That's what you can see as you are moving from this length here along the length from left hand side 1 to 2. You can see that temperature, this TH is decreasing, isn't it? So TH1 will be the higher value compared to TH2, isn't it? So therefore this minus sign is used while accounting the sensible heat of the cold fluid. So that's why this minus sign is coming in here. Okay. Now in this case, let's put this TH. Okay, so now in this case, this delta T is given by what? Delta T will be given by TH minus TC. So I can rearrange this equation and I can calculate what will be TC or TH, isn't it? So TH in this case will be what? This delta T plus TC, isn't it? This TH will be delta T plus TC, and that I can put it in this equation, in this first equation, isn't it? So dq is minus MHCpH dTH is there, isn't it? dTH is there, and TH we have calculated as delta T plus TC. So we can put that delta T plus TC in this equation and we can differentiate this. And this is just equals to the right hand side MCCpC DTC from equation 2. We can differentiate this equation. So after differentiating, what we will get? D delta T plus DTC. So that's what we have obtained. MHCpH D delta T minus MHCpH DTC. Isn't it? This minus sign is multiplied to both the factors here. So this will be the left hand side after differentiation, and right hand side. Okay, so again we can rearrange this equation. So MHCpH D delta T remain as it is, but minus MHCpH DTC, this MHCpH DTC again we can represent using this equation, isn't it? Equation 2 itself. So DTC from equation 2 will be what? dq divided by mccpc. That will be DTC. So that is what is being put here. dq by mccpc will be DTC. So this entire left hand side is first expanded after differentiating, and then MHCPH DTC is represented as MHCPH remain as it is, but DTC is nothing but dq divided by mccpc. So that is what is being put here, and this entire thing is equals to dq. So I can take this particular term on the left hand side and I can take this dq as common. So if I take this dq as common, what I remain with is 1 plus MHCPH divided by MCCPC, and that is equals to only this right hand side, which is nothing but minus MHCPH d delta t, isn't it? So dq in this case will be this right hand side divided by this entire term. So what we are going to get is minus MHCPH MCCPC divided by MHCPH plus MCCPC d delta t. That is equation number 3. Is it clear how we have obtained equation number 3? Hello?
Yes, sir.
Now in this particular equation, this dq we have already said that dq is u dA delta t, that we can put it u dA delta t, we have put it here. Now here this dA we can take u dA, we can take we can keep it on the left hand side and take this right hand side term MHCPH MCCPC divided by MHCPH MCCPC on the left hand side. So that becomes MHCPH plus MCCPC MHCPH into MCCPC into UDA, and right hand and left hand side we will be left with d delta t by delta t. So remember here this delta t term is there, but in this case right hand side here d delta t is there. So this d delta t divided by delta t is what we are going to get here after rearranging. Okay, and UDA we have taken it on the right hand side. So we have obtained equation number 4. Now equation number 4 we can integrate. Equation number 4 we can integrate between delta t1 and delta t2. Remember that this delta t is varying. This delta t is varying. Remember temperature difference. This delta t is varying from end 1 to end 2, isn't it? Correct. So we are differentiating. We are integrating this particular equation with respect to the limits. And what are the limits? At end 1, delta t is nothing but what? Delta t1. At end 2, what is delta t? Delta t2, isn't it? So that's what we have put it here. So in this integration, the limits will be delta t1 to delta t2. Similarly, if I'm moving from left hand side end to right hand side, what will be my area? Complete area, complete heat transfer area, isn't it? So that will be just A. Okay, so after integrating dA, I am going to get A. So this minus sign which was here, that I have taken on the left hand side. So after integration, what we get is ln delta t1 by delta t2 is given as MHCPH plus MCCPC. This remain constant divided by MHCPH MCCPC and UA. That's it. Is it clear to everyone? Hello?
Yes, sir.
Equation number 5 is clear. Now in equation number 5, again, let's simplify this equation number 5 further. So remember, if I apply the heat balance across the entire heat exchanger from end 1 to end 2, so sensible heat gained by the cold fluid should be same as the sensible heat lost by the hot fluid. If I take both the ends 1 and 2, isn't it? Whatever the heat gained by the cold fluid from this end 1 to end 2 should be same as the amount of heat lost by the hot fluid between the end 1 and end 2, isn't it? So that is what is equated here. Q is same as MHCPH TH1 minus TH2. That is nothing but the amount of heat lost by the hot fluid should be equals to MCCPC TC2 minus TC1. That is nothing but the amount of heat gained by the cold fluid. Now from this equation, I can take Q by MCCPC. Q by MCCPC will be what? TH1 minus TH2. Similarly, I can calculate Q by MHCPH will be what? TH1 minus TH2. Similarly, Q by MCCPC will be what? TC2 minus TC1. And both these factors I can add. So Q by MHCpH plus Q by MCCPC, if I add, only these two temperature differences will be added. If I add these two temperature differences, I can rearrange these two temperature differences. So what I can get, TH1 minus TC1, this will be the first factor, minus TH2 minus TC1, TH2 minus TC2, that will be the second factor. And what this is? What this is? This is nothing but delta T1 and this is nothing but delta T2. And if I rearrange the left hand side, what we get? Q I can take common, MHCpH plus MCCPC divided by MHCpH MCCPC. That will be equals to delta T1 minus delta T2. So this entire bracket which is given will be given by what? Delta T1 minus delta T2 by Q. So I can replace this entire bracket as what? In equation number 5, this entire initial term I can represent by what? Delta T1 minus delta T2 divided by Q. If I put it here and rearrange everything, what I get is Q equals to UA delta T1 minus delta T2 divided by ln delta T1 by delta T2. So this temperature terms, all these temperature terms are represented as nothing but what? Delta T LMTD, log mean temperature difference. So Q is obtained as UA delta T LMTD, where delta T LMTD is nothing but delta T1 minus delta T2 divided by ln delta T1 by delta T2. So this is the final expression. So you can see that whenever the temperature driving force is changing across the length, in the Newton's law of cooling, the temperature difference one should take is the log mean temperature difference. That's what we have proven, and we have proven it for the co-current flow. But if you start with the counter current flow, then also you are going to get the same expression. Same expression you are going to get. In fact, that derivation is there in the book. If you look at the derivation for the counter current flow, that is already there in the book. Is it clear to everyone? Hello?
Yes, sir.
So this is a very extremely important concept. Very often people ask this. Okay, why log mean temperature difference has to be used? That is the first question. Second question is how the log mean temperature difference is helping you to calculate the heat transfer. Remember, this delta T1 at both these ends you can calculate easily, because these temperatures are the outlet temperatures that you can find out using some temperature measurement devices, isn't it? So temperature of hot and cold fluid here and temperature of hot and cold fluid here, that you can find out. So log mean temperature difference enables you calculating the heat transfer if you know the terminal temperatures at both the ends. Okay, so delta T1 here you can calculate, delta T2 here you can calculate, and based on that you can calculate delta T LMTD, which accounts the change in this delta T across this length. So only by looking at these end values you are accounting the effect of change in the temperature across this length. Across this length. Okay. Clear to everyone? Yes or no? Is it clear to everyone?
Yes, sir.
But one more thing is there. Okay, so this entire calculation is subjected to one assumption. What is that assumption is? What is that assumption is? The assumption is this. You can see that in this case, if you rearrange dTh by dTc, if you are taking, that is given as MHCpH divided by MCCPC, isn't it? And MH, okay, 1 minute. Maybe I will explain you a little bit in a okay. So this entire assumption, entire calculation is with respect to the assumption that this U which you have started with is a constant across the length. But very often you will see that very often you will see that the U is varying across the length. When U overall heat transfer coefficient itself is varying across the length, then what you will do? Remember in this case, how the overall heat transfer coefficient will be calculated. You will look at the conduction through this particular pipe here, isn't it? Then you will look at the convection outside in the annular region. Then you will look at the convection inside the pipe here. And based on that, you will calculate the U. And U at end 1 and U at end 2, both could be different, isn't it? They may not be the same. Do you all agree or not? Do you all agree or not?
Yes.
But what we are assuming in this? What we are assuming in this? The U is constant. U we are assuming is a constant, isn't it? We have not taken this when we have used the shell. U we have taken out, isn't it? We have assumed that U is constant, but it may not be always. It may not be always. In some cases, U could be dependent along the length. So this U will be inside here. Okay. Okay. U may not be the constant. So in that case, you will get slightly complicated equation that I have not derived, but you can derive even that case where U is also varying. U is also varying. So this is one of the assumptions used in deriving everything. All right. Is it clear to everyone? Can we move further?
Sir, the U will vary because of the delta T, right?
I'll explain. Just wait. How U will be calculated?
Sir, by taking the convection of the inside hot flow.
So you will calculate the U at this end 1. What will be the U at this end 1? What are the terms which will be important? The first term will be the convection. So HI will be important here. Yes or no?
Yes, sir.
Then H naught will be important. H naught will be because of the convection which is taking place in the annular region.
Yes,
correct?
sir.
And you will have a conduction resistance through this pipe. Let's say even if you assume that the conduction resistance is negligible, but still HI and H naught you will have.
Yes, sir.
And HI and H naught may not remain constant throughout the length,
Yes, sir.
isn't it? So you might have a U slightly different value of U here and slightly different value of U at N2.
Okay, sir.
Yes or no?
Yes, sir. So the U will be a function of delta T.
So you will be, we will not be able to say directly, you will be function of delta T. What we can say is, remember in this case, the HI and H naught, this will be calculated based on the correlations, isn't it? And this HI and H naught will depend on what? This will depend on Prandtl number and Reynolds number both.
Yes, sir.
Isn't it? So Prandtl number will have the effect of what? Cp mu by K. Isn't it? So specific heat and viscosity and K, all three will be a function of temperature, some temperature, isn't it? Also this will be function of the velocity distribution, isn't it? So we will not be directly able to say that these are proportional to the temperature difference or not. This will be related to the temperature difference, but not directly. Some indirect impact will be there because of change in the viscosity, change in the thermal conductivity, change in the velocity. Is it clear?
Yes, sir.
But most of the cases we consider that U to be constant unless it is specified. Unless it is specified. Is it clear?
Yes, sir.
So, okay, so when such situation occurs when there is a, let's say if you are having a fluid here, which by halfway through, let's say, because halfway through here, it will not be there, but let's say because of halfway through, there is a phase change is taking place, let's say. So up to this, there is a liquid or gaseous is there, then it's suddenly becoming liquid. So in that case, the heat transfer coefficient will be very different. In that case, the U is going to be very different. Is it clear?
Yes, sir.
Okay. But most of the practical cases, you will see that even though the U can vary across the length, but we use the constant value of U. So this delta T LMTD, we will be using all the time without worrying too much. Is it clear to everyone? Hello? Is it clear? Okay. So there is a last concept in this entire chapter. So remember, we started with the argument that if we do the first principle modeling, things are going to become extremely complicated, and because of that the solution you will get is you will not be able to solve the equations. And therefore we said that the concept of heat transfer coefficient we have to use, isn't it? Because the concept of heat transfer coefficient you can calculate using the empirical correlations, and then you can solve only the heat transfer problem and not the flow problem at all. And even though your results will have some error, but it's okay. You are end up with getting some results instead of getting nothing. So that's okay. Now this is the additional thing. So there is another way of calculating the heat transfer coefficient. It's not only the correlation. Even though for a correlations you need to have lot of data generated initially. That data will be then converted to the correlation, and from those correlation then you will be able to calculate the heat transfer coefficients, isn't it? So that is also a slightly complicated procedure, because you will have to generate lot of data, or at least get that data from, or a correlation from some other systems. Okay, so there is another way of calculating the heat transfer coefficient by having the analogy between momentum and heat transfer. Okay, so if you are using the momentum and heat transfer analogy, then you can calculate the heat transfer coefficient, not accurately but at least fairly. Okay, so let's look at the analogy little bit in more detail here. So the momentum transfer you can represent using the Newton's law of viscosity. So Newton's law of viscosity is given here. So shear stress is given as minus mu dux by dr, where u is the velocity, change in the velocity is calculated here, dux by dr. So if you rearrange this equation, u by rho, if you take u by rho is the kinematic viscosity. So if you divide this mu by rho, you get mu by rho is a kinematic viscosity, and inside this you will get d by dr rho u. Okay, so similar to this equation, the analogous equation in the heat transfer is given by a Fourier's law of heat conduction. That is, Q is given as k dt by dr equals to, again we can divide this k by rho Cp, so we get thermal diffusivity. So that is given as d by dr rho Cp T. So both these equations are now analogous to each other, because the unit of kinematic viscosity and the thermal diffusivity both is same. Okay, again in this case the minus sign we have not used here, because the temperature of the wall we are assuming at a is higher than the temperature of the bulk of the fluid. So heat is transferred from the wall to the fluid, and because of that the minus sign is omitted here. Okay, is it clear? At least the situation, the system is clear to everyone? Hello?
Yes, sir.
Now this equation is for a laminar flow, but for a turbulent flow, these equations can be further extended by adding the eddy momentum diffusivity and eddy thermal diffusivity. So here epsilon m and epsilon h, these are nothing but eddy momentum diffusivity and eddy thermal diffusivity. So same equations are represented in terms of eddy momentum diffusivity and eddy thermal diffusivity. These are used when we are looking at turbulent flow, but these original equations are only for laminar flow. Okay, so these laminar flow equations are extended to a turbulent flow equation by adding these two additional factors. Why these two additional factors are added? Because these are bulk movement is taking place. When you are looking at the turbulent flow, a bulk movement is taking place, and that bulk movement is accounted through this eddy momentum diffusivity and eddy thermal diffusivity. Is it clear to everyone? Hello?
Yes, sir.
Now equation 1 and equation 2 both are analogous to each other. Okay. Now, so momentum transfer and heat transfer equation which we have obtained. So we are calculating the wall shear stress. Wall shear stress means if you are putting R equals to capital R, that will give us the wall shear stress. So in this equation, in equation number 1, if you are putting R equals to capital R, that gives me a wall shear stress tau W, and tau W is again related to the friction factor. Okay. So the wall shear stress is given by 1/2 F rho V square. F rho V square. Here F is nothing but the fanning friction factor. So this is related to the wall shear stress is related to the friction factor using this equation. Half F rho V square, where F is nothing but the fanning friction factor. Okay. Similarly, the wall heat flux we can obtain by putting R equals to capital R in equation 2, and that we can relate it to this heat flux at the wall we can directly obtain as HTW minus TM. That is what we can obtain by using Newton's law of cooling, isn't it? Correct? Yes or no? So heat flux at the wall can be directly obtained as HTW minus TM, where TW is the wall temperature minus TM is nothing but the cup mixing or a bulk temperature, isn't it? Okay, so QW can be obtained as HTW minus TM. Now in both these equations, equation number 1 and this equation number this equation number 1 is rearranged in terms of dimensionless velocity gradient. So dimensionless velocity gradient is what? U divided by capital V is nothing but dimensionless velocity gradient. So if I put U divided by V here and rearrange everything in this equation, what I get is minus du bar by dr at R equals to R is obtained as this is obtained as tau W divided by rho V nu plus epsilon m. Here nu is nothing but kinematic viscosity, and that is equals to Fv divided by 2 in the bracket nu plus epsilon m. So this equation number 3 we have obtained. Similar to this, the wall heat flux can also be represented in terms of the dimensionless temperature. So dimensionless temperature here is represented as T bar. T bar is given as T divided by TW minus TM. So if I put that in this original equation here and obtain dt bar by dr at R equals to R, what we get is H divided by rho Cp alpha plus epsilon H. This is what we have obtained, equation number 4. Now there are different analogies are given. So Reynolds analogy, what Reynolds analogy is saying is, Reynolds analogy is saying that the gradient of dimensionless velocity and the dimensionless temperature at the wall are equal. So what it means is this du bar by dr at R equals to R is same as dt bar by dr at R equals to R. That is what the Reynolds analogy is. So these gradients of dimensionless velocity and dimensionless temperature at the wall are equal. That is what the Reynolds has assumed. Again, what he's assumed that this nu plus epsilon m, that is nothing but the kinematic viscosity plus eddy momentum diffusivity, these are equals to alpha plus epsilon h. So with these two assumptions, if we represent these two assumptions in these equations, you can see that we can equate this Fv divided by 2V plus epsilon 2, this H by rho Cp alpha plus epsilon H, and V plus epsilon M and alpha plus epsilon H both are same. So if we put that, this alpha plus epsilon H and V plus epsilon M both are same. If we put that, we can get that, we can rearrange everything. After rearranging, what you will get is we will have F by 2 on the left hand side here, and on the right hand side we will have H by V rho Cp. H by V rho Cp is going to be there on the right hand side, and H by V rho Cp we can represent again in terms of this 3-dimensionless number, or H by rho Cp V is nothing but what? Stanton number. So by Reynolds analogy we can get Stanton number directly as F by 2. And friction factor of all the metals, everything is known. So if you know the friction factor, you can directly obtain the heat transfer coefficient. So you don't require a correlation here. By knowing the friction factor, you can calculate the heat transfer coefficient directly. So that is what the message which we are trying to give. If you are using the Reynolds analogy, we don't require even the correlations. We can directly obtain the heat transfer coefficient from this. So Stanton number is nothing but H by rho Cpv. We can take this V on this side. This alpha plus epsilon H, V plus epsilon M both will get cancelled out. So ultimately F by 2 is given as a Stanton number, and Stanton number is nothing but Nusselt number divided by Prandtl number into Reynolds number. And from this Stanton number we can calculate H directly. So if you know the friction factor, H can be calculated easily. So this is the Reynolds analogy. Now this Reynolds analogy has lot of problems because it is assuming several things. Okay. So more correct analogy is given by Prandtl, which is called as a Prandtl analogy. So Prandtl analogy is given by this particular equation. This we have not derived. I am directly giving this equation. So Stanton number is given by F by 2, 1 plus 5 under root F by 2 into Prandtl number minus 1. So it assumes the eddy transport in the turbulent core and diffusive transport in the laminar sublayer. So what it is assuming is this. I will take just one more minute and then we will stop. So if I am having a pipe here, remember in a turbulent, in a regular laminar flow, we get a velocity distribution something like this, isn't it? But what Prandtl has assumed is, in a turbulent flow, what Prandtl has assumed is this. Prandtl has assumed that in a laminar sublayer, so we will have a laminar sublayer up to this, isn't it? Up to this we are saying that the laminar sublayer will be there, but between these we are assuming that a rod-like flow is there. So this, if you look at the actual velocity profile in a turbulent flow, is very similar to this. And therefore the Prandtl analogy is more accurate compared to the Reynolds analogy.
Sir, okay. That here by rod-like means plug flow.
Yes. So by between these 2 points there is a plug flow is taking place. That's what it is. See, it assumes the eddy transport in the turbulent core. Remember, this is the turbulent core. This entire thing is the turbulent core. Is it clear?
Yes, sir.
So this is a more accurate analogy compared to the Reynolds analogy. Reynolds analogy assumes only this type of velocity profile by assuming that momentum diffusivity and kinematic viscosity will be a slightly higher value. That's it. But it assumes only this parabolic profile. That's what the Reynolds is assuming. But Prandtl has taken a more accurate picture of the actual situation, and the analogy is given by this equation. There are some more analogies given by Chilton and Colburn. These are given by these equations: Nusselt number, Reynolds number divided by Prandtl number 1/3, and that is given by f/2. Again, sometimes this f/2 can be represented using a JH factor like this, isn't it? Again, a correlation can be used for the pi flow for a friction factor. Friction factor can be obtained as 0.046 Reynolds number raised to the power minus 0.2. So if you know the Reynolds number, if you know the Prandtl number, you can calculate Nusselt number directly. That's what it is. Okay. All right. So we stop here and we will start with the sorry. Natural convection in the next class. Okay. All right. So
Thank you, sir.
thank you, everyone.
Thank you, sir.
Thank you, sir.
Yes, sir.
Thank you.